Let's calculate the generalized Gaussian integral of e to the power of minus x to the n. And we'll use the facts of gamma function, which is the following: e to the minus x, x to the s minus 1, dx equals the gamma function of s. So we'll use this identity of the gamma function. How we can get from here to here is use the fact that we can substitute x to the n for u, and the substitution will lead to x equals u to the power of 1 over n, and we'll differentiate both sides, so we get dx equals 1 to the n u 1 to the n minus 1, and this begins to look quite familiar to this. We have s minus 1 here, we have 1 over n minus 1, and we have e to the minus u. So this then leads to the integral from 0 to infinity of e to the minus u 1 over n times the integral times u 1 over n minus 1 and du. And this looks quite familiar. We can use the identity of the gamma function to get that the result is gamma function of 1 over n divided by n. And that's the result. Now we can test this out for n equals 2, for example. We know that the gamma function of a half is square root of pi, and we'll get 2 here. So we'll get if n equals 2, in that case we'll get square root of pi over 2, and that's the result. And there are values of the gamma function, for example 1 over 4, and which you'll get, for example, closed form with the elliptic constant, for example. And yeah, we have a closed form for the generalized Gaussian integral. This is quite nice. Yeah, and of course you could replace a variable, another variable, let's say a here, and you'll just get something to the front. If you want to place another variable here, it's possible, but here's the result, and we can just formalize this. So the integral from 0 to infinity of e minus x to the n dx equals gamma function of 1 over n over n. And that is the result of the generalized Gaussian.